Hello everyone, how are you doing? Welcome to another stream talk about functional programming and everything around it. A little bit clarification. Maybe this will be one of the last talks in the series. Maybe I'll make a couple more because I have a lot of work that that came recently. The work about preparing my books for production, one of them. So I will not have much time making those videos. But anyway, maybe till next September, because in August I will have a very difficult time in doing several things. But anyway, maybe in September I'll continue doing such presentations. There are maybe 10 or something like that topics to discuss. But anyway, welcome. Today we are talking about sorry, something with my voice. Today we are talking about design principles in functional programming. You might have heard about design principles in object-oriented programming. Those are SOLID, GRASP, low coupling cohesion, and many others. Are they applicable to functional programming? Are they really needed in functional languages? And does functional programming provide own design principles or not? We will figure it out today, and we'll make this topic elaborated, I would say, because people often confuse design principles, design patterns, approaches, methodologies. But what is a design principle? It's a guidance. It's a way to go in some direction. It's a compass that shows you where you can go to achieve some results. In particular, design principles are intended to make our code better in several ways. The code should be better, the design of the code, the architecture of applications and wall systems will be better in general if we follow design principles. So what design principles we can name? And what is the place of design principles in the whole system of knowledge? First of all, I would say there are methodologies that have a set of ideas on how to structure applications, how to build systems from the engineering point of view. And those methodologies have general principles embedded into them. Those general principles constitute those methodologies. For example, object-oriented design and functional declarative design. Those general principles are known as, for example, SOLID principles, or maybe keep it simple, stupid, or some others. They guide us how to structure the lower solutions, lower level solutions, such as subsystems, modules, project structure, architecture. So those general principles are above the actual coding and actual design of the application. And then implementation details follow. Those are not very important from the design point of view. We should make them like separated and isolated so that those implementation details could not ruin our design and the architecture. So this is the place of general design principles. And I propose a methodology called functional declarative design. It certainly has own design principles in it, but also I found that many if not most, of design principles from the mainstream are finally applicable to functional programming. SOLID is an acronym of 5 principles, and on a closer look, they are not about OOP or classes or Java-like interfaces. They are so general and so universal that can be applied not only in functional programming, they can be used for building something outside of programming too. For example, something in electronics, maybe even in civil construction and in other engineering fields. So those principles are universal, and we will see how to follow them when writing functional code, right? Certainly, modularity is a universal principle. Inversion of control, or IOC, is an universal principle, and IOC is naturally embedded into functional programming because we pass functions into other functions all the time, and this can be considered inversion of control. We don't call some code directly, we pass the kind of callback into internal code, and that code will call our code indirectly. So it's kind of inversion of control that exists in the skeleton of functional programming. And of course, functional languages and functional world comes with many other ideas and many other approaches. You can see domain-specific languages is a very strong field of functional programming. They can be certainly applied in object-oriented programming and in imperative programming. Absolutely magnificent tool to beat complexity. Functional programming has own interfaces, design patterns, functional programming idioms, and many other things. But today we are focusing on design principles. And we can classify design principles in several classes. First, universal design principles. Divide and conquer. This is the umbrella design principle, and all other design principles more or less follow this idea to separate things so that those things can be small enough for our brain to comprehend and isolated enough to not affect each other in unexpected way. So divide and conquer is a global and general principle that rules them all. Then we see, well, I put here make invalid states irrepresentable, which is a very important design principle in functional programming. But certainly, of course, in OOP, we also see a lot of applications and maybe even moving object-oriented languages into this direction. They are adopting features from functional languages that help to follow this principle. In particular, in particular, algebraic data types. A very interesting tool that helps us to build very consistent and properly organized domain models and make invalid states irrepresentable by construction with those algebraic data types. But that's not all, because generics and template programming and type level programming, all those things can be used to leverage this principle. It's just that in functional programming we are more close to the mathematical world, in which we literally cannot have invalid states, because invalid mathematics is not mathematics. But I would not make a point that functional programming is mathematics. It's not, but it's very close, and something comes from its mathematical nature. In particular, make invalid states irrepresentable, and a specific functional principle that is denoted here like a mathematical nature. This principle, for example, can we are investigating our domain, searching some mathematical properties in this domain, and if we are succeeded in that, we found some mathematical properties of some domain or maybe data structure, we then get a lot of good properties of this code for free, essentially. We can apply many different mathematical and pseudo mathematical concepts to that code using its mathematical properties. This is a very important design principle in functional programming, but it's not the only one. So I believe sorry. So this is the list of those principles, and let's see those principles in nutshell. Some of them, not all, because talking about all principles would be quite long. So I prepared slides with most important design principles, and we will start from SOLID for sure, and from divide and conquer. So divide and conquer. Yes, this is a principle that helps us to reason about application, not just a big pile of something, but rather a compound world of different things. They are different by nature, and the first idea is to divide our application into layers. This is a very known technique, and we should always think about what layers we are talking about, what layers we are programming, and we should not mix layers, at least without real need. This happens in big systems. This happens sometimes, and we might want to mix some of the layers together and make the code more coupled in this sense. This happens. There are reasons for that. For example, performance reasons, or maybe we don't control some system external library or framework, and this library or framework mandates us to mix several layers, for example, domain, model, and persistence. This happens, but in general, having layers properly isolated is a good practice, and it makes the architecture of the application much better. This is very important for big applications. Let's go further. And how do we divide our application? Well, yes, we first find those layers and relate our bits to those layers, and then we need to put interfaces on the boundaries between those layers, between subsystems, between notions, between concepts, and those things should interact via interfaces, not directly. This makes the whole thing less coupled. This is certainly a great idea, and in functional programming we also have interfaces. This is not about Java-like interfaces or C-sharp-like interfaces. It's not OOP. Interfaces are an important tool that it's a concept, it's a notion, and it has its own implementations for object-oriented programming and for functional programming. So we have our own interfaces in functional programming, and we use them with the same idea to make something abstract, something that lacks details, not lacks, but rather avoids details and provides a clean face for some subsystem, so that a client code could not uh, could not be coupled with the internals, with the implementation details. So we have our interfaces, and many of them can be used to, in this regard. Let's move to SOLID and see how this works. We first consider the easiest and probably the most simple of all principles, a single responsibility principle. Essentially, you don't mix many various responsibilities into one big godlike something. For example, into one big algebraic data type. You need to put all the things into those contexts to which those things really belong. For example, in here we have a sandwich method with three methods related to making a sandwich. Start sandwich, add ingredient, finish sandwich, and suddenly we have notify. What is notify here? It doesn't belong to sandwich, but we have it here, so we violate SRP. Certainly, we need to refactor our code somehow and remove this violation. Well, one of the idea is to make extra notions with the same algebraic data types. And this time I created cooking machine. I put notify into that algebraic data type, and also there is one more method there, schedule sandwich, and my program now, my recipe and program now look like completely isolated notions. I implemented some layering here. We have a layer of sandwich, which is subdomain, right? And we have a layer of cooking machine, which is another subdomain, more general domain that uses sandwich. So this is the simplest possible way to follow SRP. Yeah. Interesting that in functional programming, especially in Haskell and Scala, there are things that are yet not properly understood, that they violate single responsibility principle. I'm talking about effect systems and effect tracking. The idea of effects in FP has a very long story of some kind of scientific research. Haskellers create many different effect systems. Those effect systems essentially represent subsystems, as we call them in mainstream programming. The problem with those things is that people often mix different effects, as they call them, into one big thing, one big pile. Like here on the picture, a person, this is a real quote from a real person. A person put concurrent effect. What is concurrent effect? Put secret, put get config and logger and environment into this big effect stack. And it's not that rare when people put domain specific effects into this list near loggers, near other things, and they mix different levels of abstraction. This is very, very a very common practice in functional programming, and this makes the code much worse because it makes it unorganized. So it's another instance of how to violate single responsibility principle. OCP, open closed principle. This one is about extensibility. In OOP we have a natural way of extensibility. We have an interface and dynamic polymorphism, and we can provide various implementations of that interface and we can even substitute implementations on the fly. In functional programming, we also have interfaces, and we also have extensibility. There are even several features to make different extensible systems. And in this case, I'm demonstrating you a way to make extensible type level systems. In this particular case, it's again about sandwich and coffee and the cooking program, and those things like sandwich recipe and coffee recipe, they are very isolated. They do not know about each other and can be defined in different places in the project, or even in different projects, and not necessarily at the same time when the main program is being written, and they can be plugged into the whole system. The cooking program, it doesn't know about my sandwich and my coffee. It just provides some interfaces for making some meals, and you can plug in those things into this program and it will work. So there is a natural way of doing extensibility. I just selected this example. It's a type level programming. I selected this example to show it can be done. There are other ways. For example, we can use service handle or maybe free monad for making it on a regular value level, and we will do the same as we do it with object-oriented programming. We will make some interface from service handle or free monad, and then there are implementations of those things, and we can substitute, and those implementations are very isolated. They don't know about each other, etc., etc. Well, this is my example on the level of types. Another way to make extensible systems in Haskell in this time. So open-close principle says the system should be open for extensibility but closed for modification. In other words, there should be some core of your system that is not changing. Well, mostly not changing, but new functionality can be introduced during development independently, and can empower the whole system without affecting its core. So this is this is open close principle. Liskov substitution principle can be also applied to functional programming, because we do substitutions all the time. We put functions into other functions. For example, we put comparison operator into sort function, right? It's a functional programming. We pass a function like it's a value. And in this regard, this comparison operator may suddenly violate the contract. The sort function expects this operator to compare two values, but it doesn't expect, for example, exceptions from the operator. This would be violation of Liskov substitution principle. In general, this principle states that we can substitute interface, implementation, or implementation and another implementation, and the system will continue behaving properly. It will do different things for sure. If you have two different implementations, those implementations will perform own logic, and the outcome of those performances will be quite different, right? But there is a contract on what those things should do conceptually, in principle, and what they should not do as well. In our case, we can, for example, have console interpreter and WebUI interpreter for some terminal domain-specific language, interpretable domain-specific language. And using this language, we can write terminal scenarios, but suddenly, when we run those scenarios from application. Console interpreter we passed into application works fine, but web UI interpreter violates LSP by throwing exception. We didn't expect that. So we should always think about contracts behind our interfaces. Interface segregation principle. Again, an universal principle. We have interfaces in functional programming, and we should keep them isolated from each other. We should keep them focused on their own task without mixing them. This will help to design better systems. And this is not only just words. Do that and you will be fine, you will be happy. This is a huge experience from the mainstream, and it really works. So if we don't follow ISP for some reason, our systems become very hardly maintainable. The last principle of SOLID is dependency inversion principle, which is related to inversion of control. And this is when we have some logic that should not interact with implementation details directly, but rather should use interfaces. And when we run our application, implementation details come into that application in the form of implementations like interpreters or maybe instances of some types. In functional programming, we have this quite a lot. On the picture, we have a system that works with database and HTTP services directly, which is fine for small applications, but not for big. In big applications, we cannot avoid doing everything properly, because this particular code is not testable. We cannot, not easily testable, I would say. We cannot easily detach from HTTP services. And if we write a logic that interacts with Google, for example, we will have a problem. We call this logic from the tests and hit Google every time. This doesn't scale. So we need to detach those things to make them isolated, abstracted, and we do this with functional interfaces. Oh, sorry. So yes, those things, interface segregation principle, Liskov substitution principle, and dependency inversion principle, they are very related to each other. And this is why the SOLID principles are very important, and it's strange that we could achieve those principles. Robert Martin first coined this term and proposed the acronym of SOLID and collected those principles into one single nicely memorizable idea. So this works in our functional languages too. Low coupling, again, it's something like that as we discussed it previously, but it's another ascent of the system design. So if we have many modules, for example, and there are clients of these modules, those are modules to the left and clients to the right, there can be a very big mess if we allow clients to just reference those modules directly and without any intermediate layer. Those clients will be too much coupled with the modules and with the details in those modules. Again, this makes the code less maintainable. If you change something here in one module, all the systems to the right will change and will require your attention. If you don't control those things and rather develop your piece here to the left, you will be constantly breaking someone's work. this is not a good thing. So yes, we put interface on the boundary, and the only point through which we can access the internals, other modules, other subsystems. There is one point that we need to fix if something changed in our internals, right? And the systems and clients to the right can even be unaffected from what happens to the left. This is a very good property of properly organized code. Properly organized code allows us to change things in isolation without changing everything. In functional programming, this works too, because we have modules, we have subsystems, we have libraries, we have all the things that can be properly isolated and facaded by some notion, for example a service, or maybe interface here, or maybe top module that re-exports things from here and provides module level interface. In OCaml, for example, you have modules as interfaces, in Scala as well, and you can use them on the boundaries. High cohesion, naturally it's about having one unit of logic about one particular thing without any distractions from that thing, without external occurrences that do not belong here. So, for example, in here you see a Turing machine, let's say it's module, and this module has different algebraic data types, all of which belong to Turing machine, all of which express the idea of Turing machine and nothing else. I don't have logger here, I don't have database or whatever. I only have a way to describe my domain, which is called Turing machine. So my module is very cohesive, right? This is a good property of such units and can be applied to modules, to interfaces, to functions, to type classes, to algebraic data types, can be applied to any level of your application. Other universal design patterns: least power, Demeter's law. Oh, where is the bracket? And other. Let me first tell about dump but uniform and come razors and other design principles. Dump but uniform is about having one tool powerful enough for solving most of the problems and do not invent another solution for each small problem. This makes the code more approachable because principles used in one part of the project can easily be seen in another part of the project, and this knowledge is transferable. You can learn a small part and suddenly all the project becomes more or less understandable to you because it's uniform. Sometimes in functional programming we love doing things smarter than we should. Especially relates to Haskell and Scala, and those smart things like mathematical concepts, functors, applicatives, isomorphisms, comonads, etc., many of them, dozens and dozens. They make the code looking very strange, and you never know what else idea should be learned to understand the next piece of code, because every person does it differently and applies different concepts from different parts of mathematics and computer science and type level systems and abstract algebra and category theory. This is kind of a world map. Every country talks on each language, and even within a single country you can find various dialects, so that people in that country don't understand each other, what to say about people from different countries. And we should probably avoid that, because we need to save our time, money, and mind power, I would say, to work on the what's really important, for example, on the business projects, business logic, and should avoid bringing too much knowledge into our code. Dumb but uniform. Occam's rather also about keeping things simpler than they could be, because we can complicate our systems very much, and we can introduce many new terms, especially in functional programming, where category theory provides so many terms. But for an average person, for an average developer, those terms don't make much sense. So we should probably keep our terms more or less familiar to everyone, and we should use terms from the mainstream, such as subsystems instead of effects. Well, people will say effect is not the same as subsystem, but and when this, and then they start dissertating about what's the difference between effects and why those effects are more important from the theoretical point of view. This is all not needed really in functional programming. I mean, in average functional programming, in day-to-day functional programming. Maybe it's needed in library development, maybe it's needed in several occurrences, maybe it's needed in your project, maybe. But in general, if we want to make functional programming an industry accepted discipline, we should keep ourselves from inventing terms and notions that come from mathematics, for example, and we would rather stick to the already known notions and ideas. And this is again comes rather, do not invent new notions without real need. No perfectionism. Again, we can make mind-blowing things with functional programming. Just open any library you love, and you will see how much intelligence is used to produce that library, because people really love doing things properly and mathematically correct. But in our usual programs, we sometimes need to do dirty hacks and cut corners, and we should be able to do that without diving into perfectionism. This is again about pragmatism in general, because we need to achieve our goals. Everything should be justified from the final goals point of view, and this is what pragmatism is about. Well, let's move to least power, because it's again a kind of a coding principle, not a general philosophical principle. Least power says that a system should be written so that it doesn't touch the things it doesn't need. For example, we have a Minesweeper game, or at least its domain model. It's a very simple domain model. There are cell type and cell algebraic data types. Cell type is a bomb, count of bombs around a specific cell, or an empty cell, right? And cell can be hidden or revealed. And there is a board, which is a two-dimensional dictionary of cells. And also I made it so that I have a monad stack in Haskell. I can have 3 layers of logic in my Minesweeper game. The first layer is the bottommost, it's I/O. I can do usual operations like interacting with the user, sending data to and from database, and etc. The second layer keeps a board for me. It's a mutable, kind of mutable, actually immutable, but stateful, immutable stateful, yes, it's not a mistake, immutable stateful layer that keeps board as a state. And the third layer is again the same idea, but for scope. It's immutable stateful layer for scope. I could unify those two, certainly. I could do it differently, but the idea is to demonstrate the least power principle and the problems related to it, related to violation of it. So we have three layers. Two of them have some data attached, and I can change the data score or board, and another layer allows to do input output. Let's take a look at the function reveal cell. It gets coordinates and it asks a board from the middle layer, and then it tries to find a cell in that board, and if that board has a cell, then we can notify the user if everything is fine or if it's not. Notify failure. This is a function that I call when I reveal a bomb. Alright, let's look at that function. That function just prints it's a bomb, game over, and it prints on the bottommost layer in the I/O. But it knows too much. It knows about Minesweeper game. It knows about the whole stack of my monad. It can, in principle, update the stack, update the board. It can, in principle, update score, and we don't have such a contract here. It does too much. It knows too much and can access too many things. It has too much power, and it should be just I/O because it doesn't do anything on those layers, which is also convenient if we want to call this function from another parts of our application. In other parts, we could only have I/O, and we still can call notify failure from there if we need to. It's a question why we might need that, but it's another question, right? We could, in principle, call this least power I/O function from another places, and not only from Minesweeper game. So we made it less powerful. Demeter's law, least knowledge, is very simple to the similar to the previous principle, but I distinguish between them because least knowledge is not the same as least power. Least knowledge means some piece of code, in this particular example, a gray rectangle, should not go over the heads and access the very far piece of code that is not in the scope of this function or method. This happens quite often if we have a hierarchical domain structure and we go far inside of that hierarchy to change or to access the most internal field of the most internal notion in that hierarchy. This makes the code, in this case yellow circle, depend on this whole chain of things, and if some chain or its part changes, then the code will be broken. And also there is no clear boundary between scopes or maybe layers or maybe boundaries, right? or maybe subsystems. Those are not isolated by the fact that we use something we should not use directly. Again, the same example, we have a getting function for board, and this get function works with the middle layer. There are three layers, right? IO, middle layer with board, and top layer with score. And reveal cell depends on the middle layer here. Well, for this small example like Minesweeper game, this is fine. It will work and nothing bad will happen because we do not support this. We do not need to support this code. This code is very simple. But in general, we would like to avoid that. And we need to make some interface or maybe one single point of accessing those internals. In this particular case, it's getCell. This getCell can do the same thing as previously. It can obtain the board and maybe match the cell against those coordinates. But if we need to change the internal structure of the board, for example, this code reveal cell will remain the same. It will not be broken because getCell effectively prevents leaking the details from the inside. So this is how we remove too much knowledge from the functions and how we avoid violating the Methods law. Well, there are also paradigm defining principles, and they should be mentioned at least. Dynamic polymorphism in OOP allows us to make things pretending they are something else, for example, some interface. And this helps us to substitute things on the fly or maybe providing more functionality. We use only interfaces and we extend our system using dynamic polymorphism. In functional programming, we certainly have polymorphism. There is static polymorphism in statically typed languages, in Scala, in Haskell. There is dynamic polymorphism in Scala. It's OOP, and in Clojure it can be dynamic. Is the dynamic language, right? It can be something like duck typing, when something pretends it's another thing by the effect of its construction. So we have polymorphism in functional programming. It's just not defining property. I could put it here, but it doesn't define the functional paradigm. Encapsulation, again, it's a defining property or maybe principle of OOP when we put data and methods into some class or object, and we hide those things from the external world and allow the world to access those things indirectly, and only like that, using methods or maybe using properties like in Java and C#, not directly. In functional programming, we also have an encapsulation idea, and maybe not only one of them. We can, for example, encapsulate things into lambdas and effectively preventing the external code knowing about what was inside lambda, what we constructed it from, and use that lambda abstractly, because functions in functional programming are the simplest possible interface, functional interface. They are not the most capable interface, but still they are. So we can encapsulate things using lambdas and high order functions in this regard. But it may be a defining principle of functional programming, but not of the design, I would say, because we do it not for designing something, we do it naturally all the time. Well, inheritance in OOP, yes, we can have several notions that depend on each other and borrow ideas from the top or parent notion by chain of inheritance. Again, this works in OOP. We can simulate that in FP. We can mimic that. We mostly don't need that. We have own tools of borrowing things from other places, but inheritance is mostly about OP. Tail don't ask is about having an encapsulated object, and that object should not reveal its details and allows us to only call methods. So those methods could change the details, could change the internal data. We tell that object to change the data. We don't ask the details from the object, so we ourselves could change them. We should not do that. We should not access the internals, and we should not ask for them. Again, it's an OP thing, something of that can be used in functional programming, but still. I'll skip graphs here because it's a strange set of design patterns and principles mixed together, including low coupling, high cohesion, and there are some design patterns really. I don't understand why this set of principles is so important. It's not as successful as SOLID because it's not enough consistent. It's not a consistent set of principles, but still it exists. Well, immutability, purity, declarativity, compositionality, all of those principles are natural to functional programming, and it's difficult to say that they are about design, they are about functional programming in general. But declarativity can be a design principle. We can declare things, and especially interpretable things, interpretable declarative domain-specific languages that we then run and do stuff. It's a very powerful technique for beating complexity, and it works in functional programming, but can be used in OOP too. Well, yeah. What about mathematical nature? One simple example. We have a list of some items. Whether it's not, whether we know about that or we don't, but functional list is also a functor, and it's also an applicative. It's also a monad, and we can treat functional lists like those things, functors, monads, applicatives. Those are mathematical properties of a functional list, of a recursive structure that nests some values by in a form of a chain. And we can even be unaware of those mathematical properties, but once we discovered this idea for a list, as well as for graph, for tree, for whatever notion you like, then we have an access to a big world of nice functions, nice tools to work with those structures generically. For example, tools that work for all monads. We can work with a list as a monad. It will be an enumeration monad, and we can work with it as we do with other monads. So, but it's not necessary, right? This property is there. Functional lists is always monadic, but we are not mandated to search that mathematical nature. But if we can, we might want to do that. Well, that's probably it. Again, I'm talking about various design principles, design patterns, methodologies, and other concepts of software design in my books, and I demonstrate how to use them in practice. What are the implications of having or not having those principles, following or not following them, and how to properly structure the code, how to do architecture and design. That's it, and thank you for your attention, and see you next time. Well, maybe you have some questions I can answer, but the talk is over. Just to note that I want to edit my videos, my streams, and re-upload them as usual videos, not as streams, because streams and usual videos are treated differently by YouTube, so I'd better have both of them. Don't be scared of seeing the same videos soon when I edit them and upload to my YouTube channel. Yeah. But that's it. I think we can finish here. Thank you and bye.